In this question, we are asked to explain why the context above may not be well modeled by a binomial distribution. So let us first recall what are the conditions for a binomial distribution model. So first, there must be a fixed number of independent trials. Secondly, there are two outcomes measured by success and failure. So in this context, success or failure may mean the light bulb being defective or non-defective. And lastly, the probability of success is constant for each trial. Okay, so among this set of conditions, let us see which conditions are actually given by the question. Right? So looking at the question, we can see that we are given the probability of success. In this case, is measured by a light bulb being defective as 1 out of 200. Okay, so the probability of success is in fact constant in this question. So this is a given and not an assumption to be made. Right? Clearly, there are two outcomes in this model. Alright, so the two outcomes simply refer to the light bulbs being defective or non-defective. There is also a fixed number of trials in this question because we are told that we are taking a random sample of 180 light bulbs. So there's a fixed number of trials. So among these conditions, we can see that there is no mention of independence in the question. So we may use this to actually explain why the binomial distribution is not well modeled for this particular context. Okay, this word independence must be used correctly in your writing. Okay, when we talk about independence, we're actually talking about independent events. Okay, so it is wrong to actually talk about independent light bulbs. Alright, some students say that the light bulbs are independent of each other. It is also wrong to talk about the probability, okay, of a light bulb being defective is actually independent of another probability. Right? So you have to write out the statement correctly, okay, using the word independence. Okay. So for this question, we can say that the event of a light bulb being defective may not be independent of the event of another light bulb being defective. Alright, so over here notice that when we use the word independence, I'm referring it to the event, okay, and not the probability or the object itself. Okay. In question part 2, we are asked to determine the value of R such that the probability of accepting the batch is 0.998. So now referring to the question, it says that the batch is accepted if the sample contains less than R defective light bulbs. Okay, so let's first start off by setting up the random variable in the distribution. Right, so we can let X be the random variable for the number of defective light bulbs, okay, produced by factory A. Okay, please write in full all the words. Okay, do not use short form for random variable. Okay, some students simply just put RV. Right, this is not encouraged. during the exams, right? Okay, so defining X to be the random variable for the number of defective light bulbs produced by factory A. Now let us write down the distribution of X. So given by how X is being defined, your X actually follows a binomial distribution. Sample size N is 180, and in this case the probability of success is 1 out of 200. Okay, and back to the question, we are looking at the probability of accepting the batch to be 0.998. So from the question, the probability that X less than R has a value of 0.998, and our concern now is to find the value of R. Okay, observe that this is actually a cumulative distribution function, so we can actually use the binomial CDF in our GC to help us find the value of R. Okay, so let us look at what we can do. Now, again, probability of X less than R is 0.998. Okay, but the fact is, when we're using the binomial PDF or CDF in the GC, right, it actually starts from the value itself. So we have to change this strict inequality into an inequality that includes the equality sign. Alright, so let us convert this to probability of X less than or equal to R minus 1 equals to 0.998. Okay, and then this expression here can be entered into the GC by using the binomial CDF command. Alright, then with the sample size 180, the probability of success in this case is 1 out of 200, and this value here basically is the R minus 1. Right, so we're going to replace the R by X to enter into the GC. Right, so this is actually X minus 1. Okay, so this Y1 equation actually represents the expression for the probability of X less than or equal to R minus 1. Okay, so now we can actually use the table to generate the set of values of R that corresponds to the Y1 equation. Okay, so let us rewrite again. We are looking at probability of X less than or equal to R minus 1 equals to 0.998. Okay, so there are two columns here. You should be able to observe that the first column, which represents the X, basically refers to the R in your probability statement, and in the second column, the Y1 actually refers to the probability of X less than or equals to R minus 1. Right? So there's a subtle difference here as to whether we are talking about R or talking about R minus 1. Okay, so if that is the case, what we want is we want to aim at the value of 0.998. So if you scroll down the table, this value here is approximately 0.998 to 3 decimal places. Then what we can do is you read off the value of X in the first column, which is 5. So that tells us that your R value is actually 5, and that is the answer. Okay, now mistakes that occur in this question is such that students actually write down probability of X less than R and use this to enter into the GC binomial CDF command, okay, without realizing that this inequality must be changed to less than or equal in order to compute the correct value of R. So by doing this, okay, many students actually obtain the wrong value, which is r equals to 4. Okay, another comment is in the presentation of the solution, right? Some students just copy out this table with the column heading x and y1 without writing out what is x and what is y1, right? So you have to take note that in the event that you want to write down this table as part of the solution, you have to label the column headings appropriately. So in this case, as I've just explained, the x should be replaced by r, okay, and then the y1 should be replaced by this expression here, the probability of x less than or equal to r minus 1. So this two will provide the headings for the first and second column respectively. Okay, for question part 3, we are asked to find the probability that the batch is accepted, leaving our answer in terms of p. Okay, let's first try to understand this rather long paragraph. Right? So we start off with having a random sample from factory B. Right? Sample size is 30. It says here that if the sample contains no defective light bulbs, the batch will be accepted. Okay, and if the sample contains more than 2 defective light bulbs, the batch will be rejected. Okay, and if the sample contains 1 or 2 defective light bulbs, we are going to select a second random sample. Sample size is still 30, and the batch will be accepted only if this second sample contains no defectives. Okay, so this is the whole problem we are looking at, and we are also given the fact that factory B produces 100% defective light bulbs. Right? So in other words, the probability that a light bulb is defective produced by factory B is actually P. Now, if you are confused by the mouthful of information given in the paragraph, you can actually represent this problem by drawing a simple tree diagram, which is what some students actually did. Okay, so we started off with the sample from factory B. So what it says is if the sample contains no defective light bulbs, okay, I'll just simply write as no defects, then the batch will be accepted. Okay, if it contains more than 2 defective light bulbs, then the sample will be rejected. And if it contains 1 or 2 defective light bulbs, then we are going to draw a second sample. Okay, and if this second sample contains no defective light bulbs, then this will be accepted. Right, so from the tree diagram, it is easily seen that the batch is accepted under this condition, as well as this other branch of the tree diagram. And what we need to do now is actually to write in terms of probabilities for these two branches. Now we let y be a random variable for the number of defective light bulbs produced by factory B. Right, please use a different letter to represent the random variable. In this case, majority of the students actually use the letter B, since this is from factory B, so uses the letter B to represent the binomial distribution. But since this B, right, is the same as the B notation for binomial distribution, you are encouraged to use another letter, okay, instead of the letter B. Right, so over here we use y, okay, and y represents a binomial distribution model. The sample size here is 30. Then the probability of success, which is just the probability of getting a defective light bulb from factory B, is P. Right? Notice that this is probability and not to be left in percentage. Okay, again, some students left it as 100p%. Okay, so from the tree diagram itself, okay, our understanding is this are the two branches that we're looking at. First, the probability that there is no defect from the first sample, right? So the probability that y is 0 is actually 30 choose 0, then p power 0, 1 minus p power 30, right? So this is basically the binomial formula that you can actually find in the MF26 if you have already forgotten. Alright, so this is the formula used to calculate the binomial PDF. Okay. For the second branch, there are actually two subcases. Okay, the case where the first sample gives you one defective item and the second sample gives you 0 defective item, or the first sample gives you 2 defective items and the second sample gives you 0 defective item. Right, so for the first case where the first sample gives you 1 defective item, is given by this binomial PDF formula, right, where we have 30 choose 1 and p times of 1 minus p to the power of 29. And the second case where you have 2 defective items from the first sample, will be just 30 choose 2. Okay, and don't forget that you need to multiply to the case where the second sample actually gives you 0 defect, and that's given by this probability, right? So adding up all this, it should lead you to the final answer, which is left in terms of P. Okay, now for question part 4, we are given 40 random samples of 30 light bulbs. This means that in each sample, it consists of 30 light bulbs, and we're taking 40 such random samples, right, from each of the two factories A and B. Alright, so in other words, factory A, we have 40 samples of 30 light bulbs, and similarly for factory B, we also have another 40 samples of 30 light bulbs. So in other words, from factory A, we have a total of 1,200 light bulbs. In factory B, another 1,200 light bulbs. Okay. Now what's the question? Given that P is 0.007 and exactly one defective light bulb, find the probability that it is from factory B. So because of this word given, it gives you a clue that we are looking at conditional probability. And what is the given condition? So it is clear from the question that the given condition is the fact that there's exactly one defective light bulb. So we are actually finding the probability that it is from factory B given exactly one defective light bulb. Okay, so this is the probability that we're required to find. Now note that we are looking at 40 samples of 30 light bulbs from factory A. So what we can do is we can actually define a random variable for the total number of defective light bulbs produced by factory A, okay, out of these 40 samples of 30. So in total we have 1,200. Okay, and likewise for factory B, we are also looking at another 40 samples of 30 light bulbs. So we can define another random variable, right, for the number of defective light bulbs out of a total of 1,200 from factory B. Okay, so in this case, we can actually sum up all the light bulbs in the 40 samples. Our reason is simply because the probability of a defective light bulb in each sample is the same. Okay, so instead of considering sample by sample, we can actually consist the total number in the 40 samples that we have for each case. Okay, we let U be the random variable for the number of defective light bulbs produced by factory A, and then V be the random variable for the number of defective light bulbs produced by factory B. Right? So each of these random variables, they actually follow a binomial distribution. Right? So for U, it's binomial model, N is 1200, and the probability of a defective light bulb being produced by factory A is 1 out of 200. Okay, and then likewise for factory B, the probability of a defective light bulb produced by factory B is given by 0.007. Okay, so back to the question that we are looking at, which is a conditional prop. So we want to find the probability that light bulb that's defective is from B, given that there's exactly one defective light bulb. So now if you recall the conditional prop formula, the probability of probability of C given D is actually the probability of C intersecting D over the probability of D itself. Okay, so let us apply this formula to this question. Right, so the probability of the intersection of these two is just simply the probability that there is exactly one defective light bulb from B. Okay, but what most students miss out is the fact that not just besides looking at whether the light bulb from B is defective or not, we also have to look at the case where the sample is collected from A. So if exactly one defective light bulb from B is obtained here, what it says here is that from A there must be no defective light bulb obtained. So in other words, 0 defective light bulb from A has to be considered as well. Okay, and then this will be divided by the probability of the condition, which says that there is exactly one defective light bulb right from the samples gathered from A and B. Okay, so now let us try to convert what we understand here in words into the symbols. Okay, where we have used U and V to represent the random variables for the number of defective light bulbs produced by A and B respectively. This is what we have over here. Okay, looking at the probability that there's exactly one defective light bulb. So this one defective light bulb can either come from factory A or factory B. So we have to consider the two. Right? So in this case here, remember that U here represents the number of defective light bulbs produced by factory A, and V refers to the number of defective light bulbs produced by factory B. Okay, so we are looking at the probability that there's one defective light bulb from factory B and 0 defective light bulb from factory A. So, right, then what about the denominator, which is the probability of conditional prop? So this is separately, right? So this case will be one defective light bulb from factory B, 0 from A, or the case where we have one defective light bulb from factory A and 0 defective light bulb from factory B. Okay. So to calculate these probabilities, you can actually use the binomial PDF command in your GC, right? And the binomial formula is actually illustrated here, right? But of course, you do not need to write out this whole chunk of formula as part of the solutions. Okay, so use it correctly with your GC command to calculate the binomial PDF for each probability. plug into the formula, you should be able to obtain a value of 0.584 to 3SF.